Following on from my previous video on systematic naming, we're now going to have a look at some more examples of alkane compounds that require systematic names to be given an accurate name to show what is in their structures. So what we're going to do is have a look at our second example, which follows on from the previous video's first example. And this time, this is what our compound looks like. So we're going to have to remember our rules for systematic naming here to approach a systematic name for this compound. So if we think back, rule number 1 involved picking out what the longest chain of carbon atoms was. We've got a few choices here, so let's go through them in detail. So just like the last video, we could go through it and say, well, let's just take the one that goes right through the middle. That's always a good option to start with. So we have 1, 2, 3, 4, 5, 6 carbons going along the centre here. So the longest chain could be 6. Let's try a different way. 1, 2, 3, 4, 5. Okay, so it's not that one because that only has 5. 1, 2, 3, 4, 5, 6. Well, we could go this way and up as well. So we have a choice. We could either go right along the middle or right along nearly to the end and then up. Just like the previous video, I'm going to stick with what is the easiest to look at. So I'm going to take the blue box and put it round the longest chain in the middle. Step 2, we now need to identify each carbon in that chain by a number, and we start at the most exciting end. So I'm going to let you have a look at that, have a think. Which end do you think is the most exciting? Which end contains the most branches or functional groups? And of course it is the right hand side, because there's really nothing at all going on at this left hand side. It's just a straight chain, whereas on the right side we've got a couple of branches going on. So we're actually going to number from the right hand side this time. So we're going to go 1, 2, 3, 4, 5, 6. So already we know we have some kind of hexane here because there are 6 carbons in the longest chain. It's now just a matter of identifying, naming and numbering any branches that we have. So we have a branch here and we have a branch here. So we have a branch on carbon 2 and a branch on carbon 3. So now, given that we know the names of these branches are methyl branches because they contain 1 carbon, we have enough information to actually go ahead and systematically name this compound. So as I say, 6 carbons in the longest chain, so we know that this is some kind of hexane because it's an alkane, and we have 2 branches. Now this is slightly different from our previous example because if we have more than one of the same type of branch, we need to use a little extra prefix, which I will show you now. So we have a methyl group on carbon 2 and a methyl group on carbon 3. So we're going to indicate that by saying we have 2, 3 dash dimethyl hexane. So what have I done here? If we have multiple branches, we list the numbers that those types of branches are found on. So my methyl groups, my methyl branches are found on carbons 2 and 3. I have 2 of them, 2 methyl branches, 1 on 2, 1 on 3. Because there's 2, I can't just say methyl, I have to indicate that there's 2 by saying dimethyl. If there were 3, I would list 3 numbers of carbons that those branches were contained on, and I would say trimethyl. The idea of this prefix is just to indicate how many of the same type of branch are found on the hydrocarbon. So overall, the systematic name for this hydrocarbon is 2,3-dimethyl hexane. Let's look at another one. So this time we have a slightly different looking molecule. It looks as if it goes up and down rather than left and right. And that is important to consider because remember, atoms, molecules, compounds, they're mixtures of millions and millions and billions often of atoms, and they're all arranged relatively randomly and they all move around. So we're never going to find perfectly ordered molecules like this in nature. So we have to consider them at different angles and different shapes as well. Always imagine these things as they exist in 3D. But anyway, let's get back to the naming. So we have our longest branch, our longest chain, sorry. Let's see if we can identify that. So we could use our tried and trusted method of going across the way, and we could have 1, 2, 3. That's not really looking like the best option though. Or we could go from top to bottom, 1, 2, 3, 4. Okay, but that's not quite the longest chain, because once we get from the bottom to the top, we can then add on an extra carbon. Right, these are all in one line, and these are all in one line. So it's just a matter of choosing which direction I want to go. It doesn't matter, because it's either way I go, I'm going to have 1, 2, 3, 4, 5 carbons, or 1, 2, 3, 4, 5 carbons. So it's up to you. In this case, let's go to the right. So I'm going to draw a box around my longest chain. And then, same as before, all I need to do now is number the carbons in that chain starting at the most exciting end, and that's the side with any branches or any functional groups. So in this case, it's the side nearest this carbon, because straight away I've got this branch, whereas if I started at this side, it would take me ages to get to this branch. It would take me more carbons to get there. So I'm going to start at this side. So I'm going to have carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. And now, the last step, identify and number any branches. Here's a branch right here, and it's on carbon 2. So we know the process by now. We have a methyl branch on carbon 2, so we're going to call this 2-methyl, and it's 1, 2, 3, 4, 5 carbons in the longest chain, and it's an alkane, so it's 2-methyl pentane. And the reason why I've chosen this example is because if we think back to the previous video, this is actually the exact same compound that we named before. This here is also 2-methyl pentane. I've just drawn it slightly differently. So you can imagine that in this example, if I had went from carbon 5 here, up to carbon 2, and then out here and selected that as my longest chain, it would have looked somewhat like what we have here. It's just that this carbon up here has been twisted off to the side. So always bear that in mind. Even though they look slightly different, if you go through this process for systematic naming, and you're really careful with numbering the longest chain and selecting any branches, you will find that compounds that initially look like they might have a different structure, they might look like they are isomers, but they are in fact the same thing, or maybe even a mirror image of the same thing. And I'm going to do a video on that later on, so that we can better identify pairs of molecules that are isomers and ones that are not. But for just now, just bear in mind that you have to be very systematic and very careful with how you go through these rules, and just make sure you always select the longest chain properly, and you always name and number any branches properly as well. So what we're going to do now is we're going to move on to not naming molecules from their drawings, their structural formula, but we're going to do the opposite. We're going to look at some systematic names and see if we can come up with the drawings ourselves. So in example number 4 then, we have 3-methyl pentane. So simple enough, all we have to do is remember our 3 rules. The exact same 3 rules apply for doing this in the reverse as well, if we start with the systematic name and we want the full structural formula. So all we're going to do is start from the longest chain. How are we going to know what that is? Because it's contained in the last part of the name here, pentane. So because it's some kind of pentane, I know that I have to draw 1, 2, 3, 4, 5 carbons. Now that I've got my straight chain down, I'm going to stop there, and I'm going to go back to the name and consider where my branch has to go and what type of branch it is. And the reason I'm doing that before I draw in any extra bonds to these carbons is so that I can draw it nice and neatly, and so that I can fit things in around one another. So it says 3-methyl. So that means on carbon 3, I have to include a methyl group. Now in this case, I have 1, 2, 3, 1, 2, 3. Doesn't matter which side I approach it from, the methyl group's actually going to be bang in the middle. So I don't need so much to pay attention to numbering these carbons in this case, because the result will be the same either way. They would be mirror images of each other. So we're going to put our methyl group, let's do it going down the way this time, just for a change, because that is allowed. There's my extra carbon, there's my methyl carbon, and now what we need to do, just like we always do, is make sure every carbon has 4 things bonded to it, 4 bonds coming off of it. So in this case at the start we have 1, so we need an extra 3. This carbon already has 2, so let's include another 2. This carbon in the middle has 3, it's nearly there, so it just needs an extra 1. And we go through each carbon and do the same thing, so that we have the correct number of bonds coming off of each carbon to add to 4. And all that's left to do, because this is a hydrocarbon, is add in all of the hydrogen atoms to make this an accurate full structural formula, and make sure you don't miss any on your branches either. And there we have it, that's 3-methyl pentane. Okay, slightly trickier one then, but if we remember our rules, it should be nice and easy. This time we've got 2, 2, 4 trimethyl hexane. It seems complicated at first, but it should be nice and easy if we just go through gently using our rules. So we'll do the exact same thing. We have some kind of hexane. What does that mean? That means I need 6 carbons. 1, 2, 3, 4, 5, 6. It's ane, so it's an alkane, so they're all saturated, they're all singly bonded, so that is fine. And now we need to decide, well, which side are we going to start from, because we have 2, 2, 4 branches to deal with. And they're all methyl branches. And this time you'll notice something we've not seen yet. We have 2 of the same number. Now what does that mean? That means we have 1, 2 methyl branches, both on carbon 2, because I've used the number 2 twice to indicate that there's 2 branches on carbon 2. Okay? So let's just go from the left hand side for simplicity's sake. Let's number our carbons to keep it right. 1, 2, 3, 4, 5, 6. Once you get good at this, you don't have to actually write down the numbers, but just for just now, so it's nice and clear, I will show you those. And we need to lay out where our branches are going to be. So we have carbon 2. We have to have 1, 2 methyl groups on carbon 2. So we're going to draw in 1 at the top and 1 at the bottom. Okay, so that's that one done and that one done. Nearly there. Next step, on carbon 4, we need another methyl group. So let's just add that onto the top. I could add it onto the bottom, it doesn't really matter, as long as it's on carbon 4 directly. And now I've done my 4th methyl. So now let's count, 1, 2, 3, I have my tri-methyls. I've got 3 methyl groups ready to go. That wasn't too bad. I just need to pay attention to how many branches I have, what kind of branches they are, and where they are found on the molecule. Last step is the easy fun one. I now just need to go through every carbon that I have and make sure they all have 4 bonds. I did that nice and quick, but make sure you are counting when you're doing that process. And then of course all that remains is to make sure we add on all the hydrogens on all the bonds. And the way that I'll do this, you notice, is I will go through each carbon systematically. I'll go in order of the carbons to make sure that I don't miss anything. But you can come up with any order that you like as long as you stick to it. Now what I want to do here to finish is just to prove to you that this is an accurate way of naming these homologous series. This looks quite complicated. Are we convinced that this is definitely an alkane? How would we check that it's definitely an alkane? Well, we could use the general formula. If this is indeed an alkane, it should follow CnH2n plus 2, shouldn't it? Because that is the general formula. So let's go ahead and check. So, how many carbons do I have in total? I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I have 9 carbons. If this is indeed an alkane, I should have 9 times 2 plus another 2 hydrogens on this structure. And that way we'll know that we've done it correctly. So let's count. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 is 9 times 2, which gives me 18, plus another 2, and that's 20. So we know that this is definitely an alkane because it follows our general formula for the alkanes. And that is how we systematically name alkanes. In future videos, I will explore how to systematically name our other homologous series that we've looked at, so the alkenes and the cycloalkanes as well. But for just now, these are the basic rules that you need to follow to systematically name alkanes.